Alright, let's talk about X-rays and quantum entanglement. So, I'm not going to define what an X-ray is, we should already know what it is. Outputs photons, takes an image. So, what we're looking at here is this 2019 study titled Quantum Enhanced X-ray Detection. And this, what they basically did is they had a normal X-ray, they stuck it through a diamond crystal which split it in half. And in one half, they had an ancilla detector, which detects qubits, and in the other, they had an object detector, which is just a regular X-ray detector. And they had both hooked up to a coincidence circuit. And this coincidence circuit basically records to see how likely things are to take an accurate image. And so the individual photons recorded at the object detector were significantly more likely to align with the actual position of the atom being imaged. Significantly. Like, we're talking, like, good 30% of the data points, at least, had no chance of being where it shouldn't have been, which is pretty crazy. So, how did they do this? What is happening? So, theory behind this experiment. 1. Light acts like a wave and a particle. When we take an X-ray, we aren't using this fully to our advantage. Unpredictability in light normally leads us to a less clear image, and quantum entanglement of light particles allows us to remove this unpredictability. Basically, a beam can be split into two equal parts. We're going to call these signal and idler beams here, but these beams will have equal energies. However, an individual light photon cannot be split into two particles. It can only exist as one. So, quantum entanglement, this is basically when two particles become entangled in such a way that their quantum states cannot be described as separate from each other. For example, a photon being split into two entangled beams might have equal energy, but if you only sent 3 photons through, where did the third photon go? It entangles itself between the two beams. That's the quantum entanglement we're talking about here. And so, quick history of quantum mechanics. I'm not going to get into this now, but this is a good slide. And what we're going to talk about here is quantum wave functions. For example, light has polarization. It has H pole and V pole. That, we had glasses for that. And when light acts like a wave, these can combine into the diagonal dipole, but when they act as particles, individual photons can't combine into dipole, and normal light is a mixture of all polarizations. So, we could describe a particle's polarization at any point in time and tie it to a theoretical wave function. This is basically saying the y-axis along this is the polarization, and the x-axis is time. So, we can write the polarization and anything else as a quantum statistic. Here we have the polarization arrow, and we have a phase arrow on the right. And this just helps us write different things. But we can represent anything, not just polarization. And this is Schrodinger's wave equation. It's used for electrons. But basically it says that the wave function is super, super important for determining things. And here, we want to quantum entangle the angular frequency of momentum here, not the polarization. So, what do we want to do? We want to do the electron trick. We want to split one true electron. I'm sorry, I said electron, I meant photon. We want to send one true photon into the object detector. So, this diamond crystal acts as a unitary space, which allows the beam to split without being measured, which is just any sort of exterior interference that would mess with the quantum process. And a unitary space is just any space where quantum process can occur. But the ancilla detector measures an ancilla photon's existence, basically qubits. Any quantum sort of thing occurring there, but only one photon exists as a real particle, like we said. This means when you're detecting the qubit in the ancilla detector, the real photon must exist in the object detector. And so this records the quantum entangled photon, which has better angular momentum. The coincidence circuit records how close the taken photons are in comparison to the object's actual position. And this is this study that we saw before. And let's just take a moment to look at this kind of red box, because these are all stats that don't occur when the image is taken normally with the same beam. Like, this is not just like, oh wow, this is a random thing. Like, this is something that they did on purpose. They used quantum imaging to get this, which is pretty cool. And so, in practice, by measuring the split particle's quantum state at one location and using a diamond crystal as a unitary space, they're entangling the angular momentum of the photon in both beams. That means the signal beam can use half the light photons for imaging, and the photons will have less random angular momentum proportional to each other. This means that the light will be less random, so this increases visual contrast, leading to a better X-ray. And so, in conclusion, this is great news for hospitals with low photon beams who would be willing to invest in an ancilla detector and some unitary crystals, because the potential for clear images without adjusting the beam, like, it's pretty cool. Like, it's just pretty cool. And I think that there's a really good future using this kind of math to really help X-rays, organize their light kind of better. But yeah.